So good morning, welcome to lecture number 14, and in today's class we will be dealing about virtual memory. We did mention about virtual memory in the previous lecture. I will just recap some aspects of virtual memory that we discussed in the previous lecture and go ahead and tell you how it is implemented in a popular architecture like your x86 or the Intel and AMD. Now what is virtual memory? As I told you in the last class that I have a program which is as large as say 1 GB and I have a memory which is say 512 MB. How will I go and execute the program that is 1 GB in size on a physical memory that is less than 1 GB in size? One of the basic intuition for this is that in the entire life cycle of the program execution, if I can ensure this property that I prefer not to have a video. Can you cut out all the videos? Yeah. And you sit here. Wonderful. In the entire execution of a process, if you ensure that always at any point of time the next instruction to be executed and the data that is needed by that next instruction for it to complete execution, if these two are assured that it will be in the RAM, then eventually the program can go to completion. I repeat, the next is while a program is in execution, it is not necessary that the entire program and the entire data associated with it be loaded onto the memory. It is enough that during the entire execution of the program, at any instance of time, the next instruction to be executed and the data that is necessary for the next instruction to complete execution, if these two are available in the RAM, it is enough. And if you ensure it for every time during the execution of the program will eventually go to completion. So this implies that we can load part of the program, finish execution of it, remove it and put the next part of the program and execute that, and then remove and then go and do another part of the program. So given a program of say size K, I can split it up into smaller chunks and I load only one chunk at a time, execute it, get it back and then load the second chunk and so on. So by this, if a program is as large as size K bytes, I don't need K bytes of memory, I need much lesser size of memory. In olden days, say in late 80s and early 90s, this was done by the compiler and that technique was actually called as overlay. What is overlaying? The compiler basically takes a program, a large program, splits it up into chunks. Let me call it as part 1, part 2 and part 3, and this is the RAM. So the compiler loads part 1, the operating system loads part 1. The compiler already splits and gives the same to the OS. The OS loads part 1, executes it, then it removes part 1 and loads part 2 in the same path, then it removes part 2 and then loads part 3. So part 2 overlays on top of part 1, part 3 overlays on top of part 2. So this concept was called as overlaying, and this was done by the compiler. It was the compiler's responsibility to split this program P1, P2 into 3 parts. Please to understand that there are very big limitations in writing such a program. One cannot be very happy. A compiler has to have lot of restrictions when it wants to compile a program, and one of the major restriction in this case is that P2 should not be, no instruction of P2 should be dependent on P1, or say in mid of this P2 I can't go back to P1. If there are several points in P2 that will take you back to P1 or P3, if there are some instructions or branches or jumps which will take you back to P1 and P3, then the number of times we overlay P1 by P2 and P2 by P1 and P3, etc., the number of times this overlaying activity happens will be quite large. And so these are basic limitations. So when we want to do overlay, why I am talking about a 20-year-old technique is because you have to appreciate what the current modern technique actually offers you. So let us spend a little more time on this 20-year-old technique. When we want to do this type of overlaying, it is mandatory on the part of the compiler to see that it compiles it into 3 parts that are mutually exclusive, in the sense there is no dependency. We define dependency in this case by saying that there should not be any control transfer from P2 to P1 or P1 to P2 from any part to any other part. So when I load the part, that entire part should execute, and then I should come back, and then when another part is executing midway, I should not need any other part, because then that becomes a very complex affair. So this poses a very large restriction on the compiler, and in some sense what happens is that restriction essentially gets translated to a restriction on what? On the programmer. So the programmer is also made to write programs in such a way that the compiler can split that program into some mutually exclusive independent parts. So that is a major restriction in programming to the programmer, and there is a major constraint imposed on the programmer and on the compiler too. So based on this, the architecture, the underlying architecture, started looking at this problem seriously, and that was the basic intuition or the basic motivation for someone to look at what we call as the virtual memory concept, using what modern architectures term as paging. So in the remaining part of this class, I will explain paging. I will actually explain something called demand paging. I will explain paging or demand paging in a little more detail, so that it becomes clear to you how virtual memories are implemented in modern architecture. This demand paging uses 2 memories. One is the secondary memory, this is typically the disk, the hard disk that you have, and this is very large in size. So let us say the size of this memory for our understanding be something like 0 to some 10,000, 9,999. So totally 10,000 locations. This entire secondary memory is logically viewed. It is not that you go and cut or something. It's logically viewed as a number of partitions. Okay, let me say I have 100 partitions. I will call it as partition 1, partition 2, partition 3, partition 4 till partition 99. each is 100 partition. I said totally 10,000 locations. So the size of each partition is, in our case, 100 bytes. So totally there are 10,000 bytes in the RAM, in the secondary disk. We are allocating 10,000 bytes, and that 10,000 bytes I am splitting it into chunks or whatever, small partition, small blocks, and each block is 100 bytes. Each such block is called a page. So your secondary memory has some space for holding a large version of the primary memory or the RAM. So, and this secondary memory is split into smaller blocks. That secondary memory that is allocated for doing this is split into smaller blocks, and each block is called a page. Now your main memory RAM has only 1000 bytes, 0 to 999. So the RAM is 1/10 of secondary memory, of its secondary memory. Now I will also logically view this RAM as partitioned into again 100 bytes. So that will be F0, F1 to F9. Okay, each of this F is called a page frame. In a photo frame, you put in a photo, you can put any photo you want. Similarly, in a page frame, I can load any page I want, right? So that's why this is called a page frame, because I can put any page inside that. Now what has happened, as far as the user is concerned, he sees a memory which is as large as 10,000 bytes. But inside the system, the memory that is available is only 1000 bytes, which is 1/10 the memory that is exposed to the user. The user basically loads his program into this memory, and the operating system takes care that it transfers data from this memory to the main memory, get it executed, and keep moving the program and the data between this secondary memory and the primary memory. So the user sees 10,000 bytes, but inherently there is only 1000 bytes. So what happens here? Suppose I have a program which is occupying the space which is loaded in this memory from P2 to say P17, right? Let me say that there is a program in the memory which is loaded from P2 to P17. Let us still restrict it to P1 to P7, okay, P2 to P7. So the program in the memory is loaded from P2 to P7. Now for executing this program, the entire RAM will not be available because the RAM has some operating system, etc. Let me say that there are 3 frames available for it. Say F1, F2 and F3 are available on the RAM for the program that is loaded between P2 to P7 to get executed. correct? So what happens? The OS loads first P2, P3 and P4 as and when the program is executed. So now P2, P3 and P4 can execute. The OS loads, the compiler doesn't take care. Now what happens is first P2 is executing, then some part of P3, then some part of P2 is executed again. So there is a jump between P3 and P2. So let us see, these are the pages where your program is loaded, but this is the execution trace of your program. P2, P3, P2 is executed, then P3, then P4, then P5, then P6, then P1, sorry, then P2, then P7, then P3, then P2. Let this be an execution trace of your program. P2, first something in P2 is executed, then it goes to P3, then again it comes back to P2, then again it goes to P3, then P4, P5, P6, again it comes back to P2, then P7, then P3, then P2, then P1. So this is how the program is executed. So let me just repeat the scenario. There is a program that occupies 6 pages in your secondary memory disk version of your memory. So that will be P2, P3, P4, P5, P6, P7. It is loaded there. It is available in the secondary memory. Now for it to execute, the operating system gives it 3 frames in the primary memory, namely F1, F2, F3. Now this program essentially has, this is the way the program executes. This is the execution trace of the program, where it starts executing something on P2, then goes to P3, then again comes back to P2, then P3, P4, P5, P6, P2, P7, etc. This type of a scenario cannot be handled with overlaying. The reason is that when I load P2, then I load P3, intermediately between P3 again P2 has to be loaded, again P3 has to be loaded, and so there is going to be, in the case of overlay, the compiler actually cannot compile such a program, because the compiler, as I mentioned to you, in overlay they have to compile the program such that they are all mutually independent. Now what happens? So the compiler does not have any restriction in this case. Okay, the compiler need not care about how it compiles in this case. It just compiles as a normal program, and this is how the program executes. Now what happens? First, when P2 starts executing, the OS loads P2 into F1. Then P3 it loads into F2. Then when it executes P2, it notes that P2 is already available, it executes it there. Again when it executes P3, it knows that P3 is already available, it executes. Now it loads P4. Now it wants to load P5. It has only 3 frames, right? So it now has to replace one of this page by P5. So how will it replace? Now it will go and find out, it has different replacement policy, it will go and find out which was least recently used. So if you carefully look at the sequence, when I am reaching P5, P4 was used before, P3 was also used, P2 was the least recently used. So now P2 gets replaced by P5. Now P6 comes, P3 is replaced by P6 because it is recently used. Now again P2 comes, P4 is replaced by P3. Now P7 comes, now again P3 comes, again P2 is already there, and now P1 comes. So this is how the entire execution happens. So I will again explain this execution again. I have 6 pages of program loaded into your RAM, loaded into your secondary memory, and the operating system gives you 3 page frames for you to execute this program. First, the program starts executing at page 2. It does not find page 2 in any of these frames, any one of these frames. So this raises something called a page fault, because I could not find page 2 loaded into the memory in any of this frame. Moment the page fault comes, I load P2 into frame 1. Then I execute the instructions in P2, then I go and touch an instruction in P3. Probably even midway of executing P2, I jump to an instruction in P3. Again I find that P3 is not loaded into the memory, into the RAM. This again causes a page fault because that page is not available. So now P3 gets loaded to F2. Now again page 2 starts executing. I find that the page 2 is available in the memory. So this does not create a page fault for me. So page 2 can start executing as it is. Again I start executing page 3, again I find that the page 3 is already available in the memory, and so this does not cause a page fault. Now P4 is not available in the memory, and this causes a page fault. So in this case P2 was caused a page fault, P3 caused a page fault, P4 caused a page. After P4 gets executed, P5 has to be loaded, and P5 is not available in the memory, so there is a page fault. In addition, you see that there is no empty frame also available. The operating system has given only 3 frames for the program to execute, and an additional frame is also not available. So 2 actions have to be taken. In the previous case, when there is a page fault, the page was loaded into the available frame. Now that the frame is not available, no empty frame is available, 2 actions have to be taken. Action 1 is I have to free one of those frames and then load the requested frame. Which frame will I free? That is dictated by what you call as the page replacement policy. Page replacement policy. And one prominent such policy is the least recently used. Now when P5 wants to be loaded, please see here, between P2, P3 and P4, the least recently used is P2, because P3 was used after P2, P4 was used after P3. So P2 is the least recently used when I look at this point of time. So now P2 is replaced by P5. Then P5 gets executed, then you come to P6, again there is a page fault. Now out of P3, P4 and P5, P3 is the least recently used, so this gets replaced by P6. Then now again I get P2. So among P4, P5 and P6, P4 is recently used, so that gets replaced by P2. Now P7 comes out of P5, P6 and P2. P5 is the least recently used and that gets replaced by P7. Now P3 comes out of P6, P2 and P7. P6 is the least recently used and so that gets replaced by P3. Now again P2 comes, but P2 you already find in the memory, so this is not going to create a page fault. And then P1 comes out of P7, P3 and P2, P7 is least recently used, so P1. Okay, so this is how the entire program gets executed. So I have a program that is 6 pages in size and it got executed using 3 frames or 3 pages in the memory. So a program of size k got executed by in a memory of size k by 2. So this is the basic concept of paging. Now what we need to discuss in the remaining part of this class is how these operations are going to happen. So what are those operations? Number 1, I have to recognize a page fault. In some sense, I have to go and recognize that that page is not in memory. Right, I did. So when I started P2 was not in memory. How will I know? How will the architecture know or the CPU know that the particular page is not in memory? So in essence, I have to go and recognize the existence of a page fault. So that is point number 1. The point number 2 that we need to do is when a page is present, where is the page loaded? If there is no page fault, the page is present, where is the page loaded? For example, if you look at this, the P2 in this case, note that P2 is loaded in frame 3 at the end, but P2 was actually loaded in frame 1 to start with. So the P2 was loaded into the memory twice, one here and one at this point. When it was loaded, at this point it was loaded in frame 1, at this point it was loaded in frame 3. So any page here can get loaded into any of these 3 frames here, right? And which frame it is going to get loaded is dictated by the page replacement policy or least recently used policy. Page replacement policy or the least recently used policy in this case. So I would like to know where is the page loaded. So 2 things are important that we will see as a part of this, the remaining part of this lecture. Two things that we need to know: recognize a page fault. Number 1, I have to recognize that there is a page fault. Number 2 is, if there is no page fault, I say that the page is loaded, where it is loaded. Note that a page need not get loaded onto a fixed frame. As we had seen now, the same page 2 was loaded twice into the memory in the entire execution of the program. One time it got loaded into frame 1, another time it got loaded into frame 3, right. So to satisfy this, to actually implement this, the hardware does many of these things. The operating system is responsible for implementing this policy. So we will now go and see who is responsible for what. So if we say the page replacement policy, the PRP, this is OS. Detecting a page fault is by the hardware. This is where is the page loaded. This question is also implemented by the hardware. The page replacement policy or deciding on which frame to load what, that is which page to load in which frame, that is basically decided by the operating system, while you are recognizing a page fault or when the page is already loaded to find out where the page is loaded. These two operations are basically done by the hardware, right. So as a part of this computer organization and architecture course, we need to answer these two questions. How does the hardware recognize a page fault, and if at all there is no page fault, I go and say that the page is available in the memory, then I should know which frame it is available, right. And again I repeat, for people, since you are remote, I don't know whether you understood or not, so I keep repeating it at least 2 to 3 times. I repeat, why I need to know where the page is loaded, because a page, as we saw in this example, can be loaded into any of the frames. For example, the page P2 was initially loaded into frame 1 and later it was loaded into frame 3, right. Okay, now we will go and explain in the next 10 minutes how a page fault is recognized, and in the case the page is already loaded, how do I find the page frame where it is loaded in this context of this. This whole thing, that answering those two questions, is done by maintaining a structure called a page table. So there are, please note that there are 100 pages. So the page table has 100 entries. Say entry 0, page entry 0 to page entry 99. Page entry 0 tells two things. One bit which tells loaded in RAM or not. The other part will give you which frame. This is typically how the page table is organized. The page table in our context, I have 100 by 100 pages. Please note that I have 100 pages. For each page, I have 100 pages in my secondary memory. The user actually sees 100 pages. For each page in my page table, there is an entry, and that entry tells me whether that page is already loaded into your frame. If it is loaded, then which frame is given here. If it is not loaded, then we know that. Okay. Now let us go back to our example of, I just erased it. Let us take some other example, P2, P3, P2, P3, P4, P5, Yeah, I could reconstruct that. P6, P7. This is our execution trace. Okay. And let me now have those entries here. So I have 100 entries. So I am now bothered about P2 to P7. Now PE2, so initially to start with everything is 0. So when the program starts executing, it will see page 2. Now page 2 it will go, the hardware will go and see the page table. It finds a 0 there. Immediately it recognizes there is a page fault. Once it recognizes that there is a page fault, it goes and tells the operating system, hello, there is a page fault. Then the operating system now finds the page fault is because of what? Page 2. Now it goes and finds which frame is available and it loads to one of these frames. Without loss of generality, we say that it is loaded to frame 1. So the operating system loads this page P2 onto this page F1 and makes this one. Now the program starts executing P3. So this is page 2, sorry, F1, and this is, now it sees page 3 and there again it finds page 3 is 0. So there is a page fault. So it puts 1 here and it loads it into frame 2. So P1 is here and sorry P2 is here and P3 is here. Now when I want to execute P2, I find that this is already loaded. There is no page fault here. There is no page fault. Where is it loaded? I see it is loaded in F1. So I go to F1 in the RAM and I can execute. Then again I come to P3. I find that P3 is already loaded. Where is it loaded? In F2. I go to F2 and I execute. Now come to P4. I say there is a page fault here because it is 0. It's not loaded. I find where I should load. I put it in F3 and then. So the hardware detects the page fault and transfers control to the operating system. The operating system makes a decision of which frame should I load this, and once it loads, it comes and updates this page table with where it has loaded that particular page. So page 4 is now loaded into F3. Now page 5 comes, page 5 there is a page fault. Now again the operating system is given control. Hey, there is a page fault for P5. Now the operating system now see which is the recently used. It finds P2 is recently used. So it tries to replace P2. So it loads your P5, page 5 onto frame 1 and makes this 1 and make this 0. Since this is 0, whatever I have loaded here is irrelevant. It's invalid. Now comes P6 and you find that it is now to be replaced by P3. So P6 comes here. So P6 is now loaded at frame 2 and P3 is removed. P3 is removed. Now again P7 comes in and P4 should replace that, be replaced. So P7 is loaded at frame 3 and 4 goes off. Now again P3 comes and it should go to frame 1. P3 comes and it needs to go to frame 1. So P3 now becomes frame 1, this becomes 1, and I have replaced whom? P5, so this becomes 0. Now again P2 wants to get executed. Okay, now P2 wants to get executed, so P6 gets replaced. So P6 gets replaced, so this becomes 0 and P2 now becomes F2. Now P1 has to execute and that to replace P7. So P7 gets replaced, so that becomes 0 and this gets, what is this? P1 now becomes, okay, I have now taken another, so that now becomes frame 3. So this is how the page table is managed. The page table is managed like this, and the page table mechanism, this page table is also loaded into the main memory. So there will be, as I told you, the operating system could not give all the 10 pages to me. It only gave 10 frames, page frames to me for execution. It only gave 3 page frames, and I told you there should be some page frames that are necessary for the operating system. One such necessity is to maintain this page table itself. This page table itself will be in one of these page frames. So this page table will be in the physical memory in the operating system, in the page frames used by the operating system. So this is how we could execute a program which is twice the size of the memory onto the memory. So I had a program which was 8 frames. It used 8 frames here, P1 to P7, but I used 8 pages here, and I could execute it using just 3 frames. Okay. So with this I stop today. This is the basic concept of virtual memory. I now open up for questions. Yeah, any questions, please raise your hand. Any question, please raise your hand. Yes? Yes, please. VE cap student.
Sir, can you once again explain overlay concept?
You please increase your audio sound.
Can you please explain the overlay concept once again?
Overlay concept again. Okay. You understood this? You understood paging? Did you understand paging? Yes or no? Sorry, I can't hear you. Did you have your breakfast?
Yes, sir.
You have your breakfast. What breakfast did you have? Why are you laughing for that?
Yes, sir.
So talk loudly. See how I am talking. Talk loudly. You listen how I am talking. Talk loudly, please.
Can you once again explain the overlay concept?
Yeah, I asked you another question. Did you understand paging?
Yes, sir.
You understood paging. Good. Now explaining overlay is easy. in overlay, again I have a program which is say 100 bytes. I want to execute the same on a memory which is only 50 bytes in size. That's what has happened here, right? Now here in the case of paging, what happened? The compiler just compiled it as a normal program. The hardware took care of moving pages back and forth from memory, from the primary memory to the secondary memory and vice versa. That you understood. Now in the case of the overlay which was there when we did BTech, say late 80s, early 90s, the compiler has to take this 100 bytes and split it up into two parts, namely part 1 and part 2, such that they are 50-50 bytes. And then the compiler first will load this 50 bytes, execute it completely, and then get out this and then load this P2 on the same 50 bytes and execute it. The difference between that and the current thing is that I can't go back and forth between P1 and P2. Please note here, I did go back and forth between P2, P3. I started with P2, I went to P3, again came back to P2, then I did lot of things on other pages, again I came back to P2. This type of a thing is not possible in this because it is handled by the compiler at the stage of compilation. So the compiler has to split this program into two halves such that they are mutually independent, and so and first load P1, execute it completely, erase P1 and load P2 on top of it, that's what overlaying P2 on top of it and execute P2. Since it is handled by the compiler, there is no way by which this type of an execution trace is possible, right? So this is what we mean by overlay. Did you understand?
Yes, thank you, sir.
Good. During page replacement, is there page fault occur? What is it? During page replacement, start interest.
No.
I don't understand your question, sir.
Sir, during page replacement, if there is a page is not present, the page fault is occur or not? In this this example, you replacement, page replacement.
Why the page fault will not? The page replacement happens because. Can you reduce your volume there? My volume, it is coming. Yeah. Hello. A page fault occurs. The page replacement happens because of a page fault. So I started off with. Let me quickly explain you again. Please be with the class, okay? First, page 2 is loaded into frame 1 because page 2 is not there. There is a page fault, correct? Now page 2 is loaded into frame 1. Now page 3 is loaded into frame 3. Now page 2 is again, now let us look at the sequence. Page 2 is actually available there, no page fault here. Page 3 is available here, no page fault. Page 4 is not available, I am loading page 4 here. Now page 5 comes in, right? This is where I am going to do page replacement. So a page replacement action is initiated because there is a page fault, okay? So page 5 has to now get loaded into this one of these frames. Which frame will I load? I use some policy. For this I said we can use the least recently used policy. So when I look at this, the least recently used is page 2. So I go and replace this page 2 by page 5. Right? So a page replacement action happens because there is a page fault. Once a page fault is detected, the operating system, if it finds all the pages that are, all the frames that are allocated to it is already full, it has to go and replace one of those frames with this new page. and so it does the replacement. So your question, if I look into the chat, basically asks, during page replacement is there page fault occur? I couldn't follow. The page fault itself is, the page replacement is an action that is taken because of a page fault. So during page replacement another page fault occur. I am not able to get your question. Can you again ask me this? Having understood my explanation.
Thank you, sir.
You understood?
Yeah.
Can you explain me?
Sir, page replacement is the if the page fault when we apply page replacement.
Yeah, right. But that is the last statement. Anyway, please revise it. Which is the best replacement policy? I have a very elaborate answer, but my next teacher has come here, but I will just quickly answer you in 2 minutes. You get that video, yeah? He's asking, who is asking? Somebody asked which is the best replacement policy. The answer is very straight. For any replacement, yes.
Can you hear me, sir?
I can hear you very clearly.
Is it
Yes,
audible,
very
sir?
much. Very
Good morning,
much.
sir.
Good morning.
I would like to know what are the pros and cons of this particular method, because there
Which
are so
method?
many other methods are also used.
For which method? Is it the page replacement policy you are talking of, or the entire paging?
Just now you explained about the recently used page.
Okay.
Instead of
So
we can also go for
yeah,
the mostly.
Yeah, I understand
Mostly-
your question. Yeah, I understand your question. Now I am going to answer. So listen to me. Right? The least recently used is known to be good policy. This is again, if you ask me to prove, I can't prove it analytically. That is, mathematically I can't prove. But this is all experimentally verified and made statements, experimentally validated statements that this least recently used policy is a good policy. But for given any policy, I can always write a program that can kill that policy. Right? So if you are given some policy, say least recently used, let me say most recently used, or some average recently used, put any jargon you want, put any adjective you want and make a policy. For every policy, I can always find one example that can kill that policy. Similarly, for every policy, I can get one example which will work great in that policy. Okay. So, in some sense, this policy decision is mainly empirically driven, and that is also some of the reason why sometimes certain programs work very fast while certain programs work very slow. So, there is, it is something like you conduct an examination. Have you tested every student on every topic that you have covered in the class? No. So still there can be somebody who has only learnt half of it, but he was lucky enough to answer all those questions. But there can be someone who has learnt some 90% of it, but that remaining 10% came from what he doesn't know. So the same problem, the examination system has a lacuna. But then, what is the remedy? Do you have any other way of assessing students, especially 100 students, other than an examination? No. So you have to conduct an examination. Similarly, every policy that we put there can be one fellow who can kill that policy, there can be one fellow who can get the best use of that policy. So you don't have a real answer for that question, which is the best policy. But then I can't get away without having a policy, so I have something called a policy, right? So thousands of papers have been written on these policies. Thousands of professors have got tenure track showing that paper. Thousands of students have got their PhD. But see, ultimate analysis, nobody can come and say this is best, because always I can find a counter example that will kill it. Nobody can say it is worst, because always I can find another counter example which will make that policy work good, right? Do you understand this? So this is all about computer architecture. If you take anything like cache replacement policy, branch prediction, or anywhere where you are going to do these type of things, it is always the case that there can be something which is good, there can be something that is bad, and it depends upon which example you are trying to execute. Okay. Have I answered your question? Yes or no?